In this recording, we're going to review how to use the technique of completing the square and show how it will help us to identify transformations, specifically the shifts or the translations that a graph will make from the parent function. Okay, so we can see the parent function here, y equals x squared, and we're interested in knowing, well, I've got this other function here, which is not y equals x squared. What are its transformations? Can I get it into this form where I can identify the coordinates of the vertex, the h and the k? So we're going to use completing the square, which is a technique you had from Algebra 1, but you've probably forgotten. You haven't used it in a while. Let me just review that for you. So we're going to start out this way. We're going to write out y equals, and then I'm going to group together the first two terms, the x squared minus the 8x. And I'm going to keep that 18 over to the side for later. So I'm going to specifically focus on the x squared minus 8x. And basically I want to create this square. And in this square, I want to have the same dimensions, which makes it a square, right? So I want to have my x squared. In order for these dimensions to be the same, I'm going to split the negative 8x in half. So negative 4x and negative 4x. We're going to do this every single time. Obviously, it works better when it's an even number because these become integers, but we can even do it with non-even numbers. We just have to take half of it. You can take half of anything. So we've got x squared. I'm sorry, we do not. We have x, and we have x. And then, of course, this is negative 4, right, to produce the negative 4x and negative 4. You can see it's a square, right? X minus 4, x minus 4. What number needs to go there? Well, 16, because it's the negative 4 times negative 4. So, back over here, when I express this now, I've got y equals x squared minus 8x plus a 16. I want to add in that 16. This is the 16 that completes it to make it a perfect square trinomial. Plus 18. And now to keep it balanced, I can't just add in a 16, right? Unless I also subtract 16. So the net value of adding and subtracting 16 is neutral, right? Adds to 0. So I can do that, right? I can add 0 anytime I like. But now what you've got in parentheses is a perfect square trinomial. You can see it's factored right here, x minus 4, x minus 4. So I can express it as x minus 4 squared. And I can just simply add these two terms and get a 2. All right. So I can see, all right, that's cool. Now I can see the vertex is at 4, 2. Right? Talk about the shifts. Well, we know this shifts 4 to the right. Right? We've known that from other functions that we've studied. And it asks us, okay, what would be the vertex? Well, I can tell that if I take any of these points and shift them 4 to the right, 1, 2, 3, 4, and up 2, now my new vertex is at 4, 2. So it says sketch the graph. So I'll speed that graph up, and you should make the graph as well. Take all your points and shift them the same, 4 to the right and 2 up. And now I'm just going to name this function. So this is y equals x squared minus 8x plus 18. Anytime we have two graphs on the same function, remember we want to label them. And this was just our parent function, y equals x squared. Cool. Next it says, use your calculator. We're trying to make a point here that all of these functions that are of the form y equals ax squared have the same turning point. So let's just graph 3 of them so we can see some of the common features. Basically compare and contrast here. So we're going to grab our calculator. If you have a calculator, please use it. If you don't, you can just play along. So we're going to go into our calculator, and I'll kind of speed this up. The putting of these into y equals, and then getting the window set up from negative 5 to 5 in the x, and negative 5 to 15 in the y. Now we're just going to set up our window, press the window key, and negative 5 to 5, and in the y, then just hit graph. So I'm going to cheat and just paste that in here, and just label each one of those. And I'd like you to copy that graph down onto your paper so we know that this innermost one was y equals 3x squared. The red one is the parent function. Excuse me, just x squared. Okay, so the 3 made it stretch vertically. The 1/2 made it compress vertically. And finally, the point of doing this was just so we could examine the fact that even though they are stretched differently, they all have a turning point at 0, 0. In our next video that relates to this, we're going to examine the effect of shifting right and left and how that relates to vertex forming completing the square. Thanks for watching.